Well, thank you very much for that introduction. Happy to be here, and it's my pleasure to start us off this late morning. So to get things going here, what are gravitational waves? So we know in general relativity that mass will bend space-time, and if you get masses that are orbiting around each other, they will in fact emit gravitational waves. So to motivate what gravitational waves kind of look like, we're going to imagine that you have a gravitational wave passing into the screen, and you have a set of dust particles that are just floating there. And as they pass through, they will oscillate like this. Of course, they can also oscillate like that. That seems pretty straightforward. What that motivates, though, is a design of an instrument. This is a very simplified view of what we actually do. So we have a laser that's split into two beams. We can measure, as the two arms change length, the difference in light between the two beams. I'm going to play this animation once more. And you can see that the light is split into two. It comes back. It is combined. And as the arms change length, you'll have deconstructive and constructive interference. And that is what we can then measure. And of course, it's not just theoretical. We built these instruments. My clicker appears to. Let's go on the next slide. Okay. So this is the LIGO Hanford instrument. It's 4 kilometers long. We have its sister in Livingston, Louisiana. And of course, in Europe, we have the Virgo Observatory of 3 kilometers. So you see, we need these huge sizes to be able to detect these sort of signals. And we also have, an upcoming network of observatories. So under construction is the Kagra Observatory in Japan, and being planned and will be constructed hopefully soon is another detector in LIGO in India. Okay, and again, this is not just theoretical. We made our first detection back in 2015, in September. What we see is consistent with a 36 solar mass black hole merging with a 29 solar mass black hole. And to give you an idea, this is the time series of the signal we observe in units of, here's in units of strain. So this is how much relative length the instrument is changing. And here's a time frequency representation. You can see a couple interesting features of this that are worth noting. One is that as you progress in time, the frequency is increasing, but so is the amplitude. And so you have a couple different parts of the waveform which you can point out. This is what we typically call an in-spiral. So there's objects orbiting around each other, and then they merge together, they become one object, and that object sort of rings down, which you see at the end. Now, it's not the only thing we've seen. I'm sure most people here, if you've been following the science news, know that we have also recently discovered a binary neutron star merger just back in August. And most importantly, this also coincided with the observation of a gamma ray burst at the same time. And again, you can see it's a very clear signal for us. You can see the time frequency track here. You'll notice a few differences here. It's a much longer signal than our binary black hole signals. But this one, again, we lucked out, it's extremely clear. Now, what I'm going to try to do here, I'm going to need everyone to be really quiet. We're going to actually listen to an audio of the data. Since our data is essentially just a time series, we can, of course, pipe it to speakers and use your own auditory equipment to try to disentangle this. And I will warn you, this is not easy. You'll expect to hear something only towards the end, okay? And I want you guys to listen very closely and see if you can hear the signal. So you're not going to hear anything now. This is just the instrumental noise. But you will start seeing in the time frequency spectrogram, start seeing the signal. But your ears only pick it up very close to the end. That's it. That was the signal. As converted, that was our real detector data converted to audio, and you can use your own ears to in fact hear it. see if I can actually pause that. Okay, so it's spanning about, the part that is actually sort of visible to us is spanning from about 25 hertz up to 500, 600, 700 hertz. It's, in fact, going far beyond that. We can't actually observe as high frequency as it will actually merge. So we're really just seeing basically the in spiral. It will merge at, say, several kilohertz, but we can't actually observe that part of the signal because it's just, our instrument isn't sensitive to those frequencies. Okay. Okay, but not, again, the miraculous thing about this event is not that we, of course, can just see the gravitational waves, but you can also see in light. So this is actual telescope observation, and you can see this little flash of light here. This is the electromagnetic counterpart to this merger. And here is what we think, this is an artistic sort of representation of what, if you were nearby, you might have seen, although you wouldn't have seen these little lines coming off, but some, artistic license taken. That's something like what we think would have happened. Okay, but we haven't just seen those two signals. This is what we've seen so far. So we have a number of, these are binary black hole signals. These are the gravitational waveforms that we actually see in the detector. And of course, this is the binary neutron, so it's much longer. It goes way off the page for another 50 seconds or so. But now we can go, well, these aren't the only kind of things we're looking for. I am going to focus today on compact binary mergers, but we are also looking for continuous waves from spinning neutron stars, some unmonocoherent bursts, supernova, stochastic background. But again, today I'm going to focus on compact binary mergers. So how do we look for these? Well, we have a model for what the signal looks like. You saw a couple of those in the previous slide. So we know what the signals look like. So if I tell you what, for example, a neutron star has this mass and this mass, I can tell you what the gravitational wave signal will look like up to the point which they merge. And we can use that knowledge, use a very standard technique that originates out of Doppler, which is use match filtering. So you have a model of the signal, you have your detector data, and you have maybe some signal that's embedded in the noise. And then you convolve them together and weight by the detector noise, and you can calculate an SNR time series. And what's nice about this is it's known to be the optimal technique if you have Gaussian noise. We'll hear in later talks that this is not necessarily the case, and some of the things we do to try to work around that. But for now, this is sort of the critical component of how we search for these kinds of signals. Now, the key thing here, though, is that we need to have a model for the signal. And importantly, we need to use a model for every type of signal we want to look for. So what we do is we create a collection of different waveforms called a bank of templates that represent any kind of system we could possibly find. And for very simplified purposes, what we currently do is we have essentially 4 parameters which describe our waveforms. There are, of course, many more, but we do not include all of the physics. We focus on the component masses of the binary, okay, and then also the spin. So each object, of course, can rotate along its own axis, and we include that effect as well. We don't include, notably, the effect of any sort of spin off axis. So it has to be sort of aligned with the angular momentum. If it's off axis, you might be familiar that you might get some precession effects as it orbits around. We normally don't include that. Now, one thing is, for the current searches, to search sort of a very wide range of masses, so this is between 1 solar mass and up to 100 solar masses and even more, is we need about 400,000 templates for the current analysis. That increases dramatically over the next few years, because this is related to how sensitive our instrument is and how fine we can tell the difference between different kinds of signals. So this will increase by order of magnitude up to the point we get to the design sensitivity. Now, to give you guys an idea how this works, I'm going to give sort of a very obvious example. We have our template waveform, and it's sifting through the data. And you're going to see here, actually, the signal in the data. This is the first event binary black hole merger we saw. And of course, it's also very clear in the data just by eye. And you can see that we can use this sort of template filtering method to extract the signal. Now, this is not necessarily the best example because this signal is honking loud. Some grad students and some microphones could probably sit in a room and probably detect this thing. But that's not the purpose. You're going to have signals that are, of course, much quieter, and different types of signals that are much harder to extract. For example, this is a lower mass signal. This is a signal that we detected on December 26th in 2015. It's also a binary black hole merger. And this one, I don't think you're going to be able to see in the data, but you'll be able to see it very clearly right there in the match filter. So that's why we do this. You look out once in a while and you can actually see it, you can detect these things other ways, but if you want to detect quiet signals, you want to detect as many as you're going to be able to find in principle, you need to use these sort of methods. Okay, so I can break down the basic idea into a procedure. So we have a model of the signal. There's a bunch of different ways for getting this. You can post-Newtonian, analytical, and numerical relativity. We're going to have a talk later on numerical relativity and how we actually can model these signals in principle. So please look forward to that talk. For our purposes, we often use phenomenological things which are tuned to numerical relativity so that we have something that can be cheaply produced. Because one of the things you're going to hear about is it's not a trivial process to generate these numerical simulations. So we can't generate, say, an infinite number of them infinitely cheaply. Okay, so then we use a match filtering to look for signals and generate an SNR time series. And then, of course, we do a number of checks. I'm not going to cover a lot of these today. I'm going to focus on match filtering because that's where the core of the computational cost is. But just to give you an idea of things that we actually look for, we, of course, check that we see signals in multiple observatories. We check for consistency between the observatories. We check that the signal we're seeing has the right morphology of a real signal. And we look for other confounding factors. And Andy in his talk will talk about a number of things that can possibly go wrong and ways we deal with that. And, of course, we need to estimate the statistical significance. I can break what we do into sort of two regimes. We have offline detection. These are our deepest analyses. These are things we can sit around and ponder and try to do our best jobs we can. And they really take advantage of our best knowledge of the data. We also have low latency detection. This is critical if we want to be able to coordinate with astronomers and make detections like we did with this binary neutron star merger. Because we need to be able to tell astronomers where to point their telescopes. So we need to be able to detect something in seconds and then tell astronomers where to point. And that involves different problems. Offline detection, you might have surmised, but this is actually something that's extremely parallel. Each template can be analyzed on its own. If you're talking about something that you have archival data for, you can, of course, break that data up into chunks and analyze those separately. So this is what we call a really embarrassingly parallel problem. And so typically one of our jobs is to try to map this problem to as many computing resources as we can. And we do that in a couple ways. The thing that really helps us is we use what's called workflow management system. We use one from Pegasus, which allows us to describe the kind of work we need to do and do so in an abstract way, which we can then map to different types of resources. These are things like batch submission systems on clusters that use either HGC Condor, Slurm, PBS, similar kinds of systems. And so we can have each of those handle a particular task. The task will usually be something like analyze this segment of time and look for these kinds of signals. And each of them can do that separately, and we usually have order 10 to the 5, 10 to the 6 such tasks. And just to give you an idea of how much computing that actually requires, for the O2 analysis, we use roughly 200 million, or roughly 100 million core hours. We expect that to maybe double for our next analysis. So to give you an idea, we have a number of computing resources that we can take advantage of. We have dedicated clusters that are part of the LIGO laboratory systems. We have LHO, LLO, and CIT. We have, as part of the LIGO scientific collaboration, we have a number of other contributed clusters in yellow here. And of course, one of the things we're trying to take advantage of, and I'll talk about a bit more, is the open science grid. So to maybe give you an accounting for that, give you an idea, we have the LIGO data grid, which includes these dedicated lab clusters and the LC clusters. That we have access to about 40,000 cores that we can make use of. Recently, we've been trying to get more computing done on the open science grid. And that has been about 20% of our computing usage up to this point. So most of it, as you can tell, is on our own dedicated resources. But we are shifting more and more of it to the open science grid. And that is nice because it allows us to use a number of additional resources, often which are shared amongst PIs. So we have a number of resources that are available in Europe for this purpose. A lot of individual researchers have, say, resources at their own institutions, which can in fact be contributed in this way. We have things like campus and regional shared networks. The campus networks are kind of neat because those are the ones where, for example, the secretary's office computer, when they're not working, reboots at night into a virtual machine, and then actually we can submit jobs to. So that one's actually kind of a fun one. And of course, it also allows us to run at the national supercomputers. In particular, we've done testing on Exceed, Stampede, and a few other places. And I just want to point out another resource that we do have, although we don't make use of it for this kind of analysis, is we also have Einstein at Home. And this is very similar. I'm sure people have probably heard of Folding at Home or some of these other programs. It's very analogous. We use the same technology. And people can search for pulsars and spinning neutron stars on this analysis. And that provides us, we have about 40,000 active users. In total, there's about an order of magnitude more who are not so active. And you get about 5 petaflops of performance from that. But again, we primarily focus on searching for pulsars and spinning neutron stars from that. So one of the areas we've been trying to move to is to move to more computation on the open science grid. That's an initiative we've been sort of pushed towards by the National Science Foundation in the United States. It has some advantages in that there are many clusters that participate. But each cluster essentially has its own rules for how it participates. So they may have some resources which they make available if no one else is using it. You may have a dedicated allocation that you have applied for at that university, et cetera. We can handle all of that. And in fact, in general, when we end up running on about a dozen different clusters across the country, and in fact, across the world at this point. This is probably sounds like small potatoes for what some people are used to in computation, but our data set corresponds to about 5 terabytes of data. You'll remember that our data is essentially an audio stream, and it's an audio stream level bit rate too. It's only 16 kilohertz, so it's actually not even high quality audio. So we transfer this. What we do is we transfer this to a central server, and we store it under what's called a CERN virtual file system. And we so far have clocked in about a petabyte of data transfer. This is because each of our analyses need to access some of the data multiple times to actually complete its work. And we've been lucky enough that we can get away with relatively reasonable strains on that server, roughly about 10 gigabits per second sustained. Now, one of the issues that you do arise when you run in this kind of environment is each of these clusters has a slightly different software situation. They have a different software stack. They have different hardware, very different hardware. And so one of the things we've had to move to is our software has to be containerized. So we have 2 different ways we have done this. One is by using virtual machines. And then the other that's more useful for us is actually using Docker images. So we actually produce Docker images of all of our code and source environments so that you can run in these sort of places. So what I've talked about so far is basically how do we get our stuff to run everywhere. I haven't said anything about how do we actually get it run well. So there's a couple things to keep in mind. As I said, all the computational cost is basically in the match filtering calculation. What does that entail? It entails a couple things. We need to generate a template waveform that we're trying to look for. We need to do a correlation, which is in frequency domain, it's just a complex multiplication. We need to do a fast Fourier transform, because if people know their convolution theorem, you can do convolution by a nice Fourier, you can do it by a frequency multiplication and Fourier transform. So this is a very efficient way to calculate match filtering for many different time points for us. And this, in fact, ends up being the largest part of the computation is the fast Fourier transform. And so the first thing we use is, of course, we use other people's work. So we use the well-optimized FFTW library, which also allows you to optimize for the hardware you're on. And where possible, we also use the Intel math kernel library. And of course, the other things we do are things like peak finding. In general, though, the 2 areas of real concern are template generation and fast Fourier transform. And you might realize right now that an obvious thing to do would be to run this all on graphics processors. And in principle, this is a really great idea. We have been porting our code to run on CUDA. We decided to focus on CUDA largely because of the availability of hardware we had within our own LIGO data grid, which was largely NVIDIA hardware. We've also focused largely on consumer GPUs for a number of reasons. One is they're a lot cheaper. The bigger thing for us is that we don't care about double precision performance. We only care about single precision, and we don't need a lot of memory. So we just need a lot of computation and for as cheap a space as possible. And of course, there's the well-supported, well-optimized library which NVIDIA provides, the CUFFT library, which is very excellent. So the kernels I just mentioned are largely ported with one exception, which is somewhat difficult, and that's the template generation. So this is the thing we actually need to be correct. This is what we expect the signal to look like. We need this to actually be able to find it in the data. Now, one of the problems is that this is a constantly evolving field. So, as time goes on, people are developing new models for gravitational waves that include new and better physics. And one of the things that happens is that by the time we've implemented a GPU version, it's already out of date. And as far as we can tell, it always will be. So we've given up on that. We're not going to bother trying to implement that anymore. But we can leverage a few things we do have to an advantage. One is that when we're doing a search, we know exactly the kind of systems we're going to look for. We know that before we're going to do the analysis. And so we can do things that are just one-time upfront costs. And one of those things we can do is to essentially take our waveform. This is what it looks like in the frequency domain. You've seen what it looks like in the time domain. But this is what it looks like in the frequency domain. One of the things you can realize is that if you separate out, has this oscillatory pattern, you can separate it out into an amplitude component and a phase component. And you'll notice that these are very nice, smooth functions. And what we can do is we can approximate these just by linear interpolation. And so what we'll do is we pre-compute all of these for every system we want to look for ahead of time. We then create a set of interpolation points. And these are a few orders of magnitude smaller than the actual amount of templates themselves, enough that we can actually store every single template on the GPU up front and just load them once at the beginning of an operation. And then do the interpolation, which is extremely fast, on the GPU. So that's what we've done. And we don't have to do any of the template generation on the GPU. We can just do some very cheap linear interpolation. It's a very simple operation. OK, so we've done some testing with this. The initial testing says we get about 5 times performance improvement with relatively cheap consumer cards. We know this is not optimal. There's a couple of reasons for that. One of the highest reasons is that other parts of the code are bottlenecks into the higher level parts of the code. And so we already have plans to do some reorganization of this to try to do more batch processing, reordering some tasks, but it's already going along the right route. So this is an area we're going to be looking into more and more into the future. OK, so now I'm going to want to switch gears here. That's the offline analysis. How do we detect things in low latency? There, we can't farm out work to a dozen clusters around the world. That's not going to work. We need an answer pretty much now. And we need it for a number of reasons. We need it because we need to be able to find things like this. And these things eventually will disappear. We need to produce this sky localization. So this green area right here is what we actually sent to astronomers to try to find this event. And they were able to find it right here. So it was very useful for that. And so we need to be able to detect these signals within tens of seconds and be able to tell the astronomers where to look so they can try to find the corresponding signal. And so I'm going to sort of sketch out how this works. So we have data collected at our sites. So we have a site here. And again, the one at Livingston, of course, we have Virgo here. This data is aggregated at Caltech. And then it is streamed to a couple places. One of them is in AEI Hanover, where I work. Also, analysis is done at UW-Madison. And we stream the data there using standard internet protocols. And then the magic happens when we get to the other end, where we distribute the data via multicast. I'm going to sketch out basically how analysis proceeds when you do this. And this gives you a basic idea of how you're doing it. It's not particularly tricky. The basic idea is that we have some potential signal in the data. And then all we do is we look for some segment of time, which we're going to try to analyze. And this data is actually streaming in. And we determine that we're going to analyze this chunk of data when it's available. And some of this you're going to lose. And that's because we have to do filtering on it. people have questions, I can, of course, discuss what kind of filtering we actually need to do. But the point is, we do need to apply filters to the data before we can analyze it, and you lose some of that due to filtering corruption. But we essentially analyze the segmented data, and we produce results for very small chunks, so say 8 seconds. And what we do is we look for every template in that 8 seconds. And I can talk about how we do that effectively in a second. But then the idea is when we complete this, we've now given you 8 seconds of results, and we try to do that in less than 8 seconds. And then we proceed on to the next chunk. So it's very much, you look at some segment at a time, and then you look at the next one, it proceeds very naturally. Now, you could ask, how do we actually do that in guarantee that it happens fast enough? Well, the way you do that is we farm it out to many computers. We have a dedicated set of computers just for this task. We use MPI to parallelize this task over multiple nodes. And within each node, we use OpenMP to parallelize amongst the processors of those nodes. Each of these nodes is doing a symmetric operation. They're just match filtering a particular portion of the template bank, looking for a certain set of signals. And they report back results to a central place, which we then collect together, see if there's anything interesting, and then submit it on to our central server, which we will then alert astronomers if there's anything interesting. So one thing that's interesting about this is that you can actually do this in only about 160 cores for roughly 360,000 templates, which is how much we needed for O2. That turns out to be relatively tractable. And the whole operation from the gravitational wave passing through our detectors and actually moving the instrument to us being able to report something is roughly 30 seconds. Now, for the past few runs, the longest part has actually been after we see something we have been through a human vetting process. We've actually gotten people together to look at it before we actually alert anyone. But in principle, this is roughly what you can expect down the line. So in summary, we have offline analyses, which are embarrassingly parallel. We use tools like Pegasus and the Open Science Grid to farm these out to many different clusters. We also do online analyses, which are critical for actually telling astronomers where to point and find electromagnetic signals to our mergers. But these require dedicated resources. And the reason they require dedicated resources is because we need to actually be able to enforce our latency requirements. And you can't do that when you have opportunistic resources. And I think I'm going to leave you with one last thought. Is, of course, I do want to highlight some of the open science that people are doing and some of the open software we have. Of course, the LIGO data itself is released through the Open Science Center at lost.ligo.org. It's soon to be renamed WASC, because we have, of course, Virgo joining us, and we'll be also releasing data. And, of course, there'll be future detectors down the line. The majority of the LIGO analysis codes are, in fact, open sourced and available for people to use. You can get many of them at lost.ligo.org's software. One of the ones I'm involved with is called PyCBC. You can get information here. We have tutorials, and of course, it's available on GitHub. And I think probably there I can open up for questions. I think probably out of time as well.